This is the Open Enzo, and today I'm going to be covering identity matrix and matrix inversion. So let's start with the identity matrix. Identity matrix is a very important matrix, and it's represented as a big I, just like this one. And in the two-dimensional world, an identity matrix I, where it's a two-dimensional world, looks something like this. It's always a square matrix. There's always ones along the diagonal, and all other values are 0. For example, in the third three-dimensional world, again, it's going to be a square, so a 3 by 3 matrix, and all ones along the diagonal. This by the way is called a diagonal if I haven't covered that before, and all other values are 0. And what this matrix does is that if you multiply this matrix by any other matrix, so for example, this is the identity matrix and this is any other matrix, this will equal to the matrix itself. It's sort of like in scalar values when you just multiply something by 1 equals the value itself. It's the same with matrices. This is like the scalar value 1 for matrices. So if you multiply that, you're going to get the matrix, the original matrix, and it doesn't matter the order you multiply it in. Like I said before, the order you multiply it in, multiply matrices, it does matter because matrices are not commutative, but not in the case of identity matrix. Now, one of the reasons I told you guys about the identity matrix is that it helps us understand matrix inversion, along with its other nice little properties, but I won't be covering that today. Now let's say that we have a matrix A. The inverse of this matrix A is another matrix which looks something like this. And when you multiply these two matrices together, the matrix and the inverse of the matrix, you always get the identity matrix. You can somewhat relate this to division by self in scalar quantities. So something like 3 divided by 3 equals 1, because 1 by 3 is the inverse of 3, right? Same way, maybe not the exact same, but similarly, this a matrix and its inverse multiplied by itself is the identity matrix. Now, one property is that this guy, not all matrices have an inverse. Now, how can we relate something like matrix inversion to the world of game programming? So another way you can visualize matrix inversion is that, let's say we have a vector P. Now let's say this vector rotates. It's a transformation vector, and it rotates an object when multiplied by it by 70 degrees, a positive 70 degrees on the z-axis. Now let's say we find the inverse of this matrix, which is this guy right here. If we do this, now let's say that we've multiplied this matrix P to an object, and now it has rotated 70 degrees on the z-axis. Now let's say we do something like, first we did PA, and let's say the product of this was, let's say, Z. Now let's say we do P, the inverse of P multiplied by Z. Now, due to this property, this is something like P, PZ, P negative 1, and these two cancel out, and we get the original matrix itself. And in what this means in the game programming world is that we actually undid the effects of the first transformation matrix. So what this matrix really stands for is that rotating negative 70 degrees along the z-axis. So undoing the effects of this matrix undoes the effects of this matrix. And what I mean by positive and negative is just if this was clockwise, this would be counterclockwise, just the exact opposite direction. Okay, one thing I want to correct is that I made a big mistake right here. This guy right here is totally incorrect. Doing this does not result in the vector z, and plus this should have been a anyways. So when you multiply p negative 1 by z over here, the inverse of p, this is something like the inverse of p multiplied by p a. And I'm so happy that I made this mistake, because in the previous tutorials I stressed the importance of the order of multiplication of matrices. Because if I did something like AP A and I did something like AAP, and these are just three random this is the same matrix A, and these two would result in a totally different product. They would not be the same product, and that's due to the property of that matrices are not commutative. So this should look something like this, and the inverse of p and p cancel out, and then we're left with the right answer right here. So +1 for doing mistakes during my videos. Now that I've talked about inverses, there's one thing left, and that's the inverse of concatenated matrices. Like I discussed before, we use concatenated matrices for various things, and they look something like this, where we have an n number of matrices being multiplied together. Let's say we want to find the inverse of this. The inverse of this would be, first we want to reverse concatenate this. So we want to concatenate this in the reverse order, and that would look something like this. And they're still being multiplied. And the inverse of that would be the individual inverse of this product of each matrix. So in one sentence, we're doing, to find the inverse matrix of the original matrix, we're doing the individual inverse of the reverse concatenated product. Now that's it for today's video, and please subscribe to my channel and give me some feedback.